All right, hello everybody. My name is Stephen Czyz. I'm from Oregon State, and today I'm going to be talking to you guys about the development of a radio-xenon detection system using CVT, an array of SIPMs, and a plastic scintillator. So first I just want to go over a little bit of an outline of what we're going to be talking about. I'm going to talk about why we are detecting radio-xenon and why specifically beta-gamma coincidence. I'm going to talk about the results from our first prototype system, the two-element CZT detector. We presented a few of these results at the last workshop, but we've since conducted more measurements and we want to talk about those. I'm going to talk about the pros and cons of that system and why we designed a new prototype system, the CASP system. I'm going to look at the measurements that we did with that system so far, some conclusions, and outlook for the future. So, when a detonation occurs, radioactive xenon is released into the atmosphere. And the International Monitoring System, which is an array of systems all around the world established by the Comprehensive Test Ban Treaty Organization, needs to be able to detect these radioxenons at extremely low concentrations, less than 1 millibecquerel per meter cubed of air. And this is what's called the minimum detectable concentration. So many of these detection systems take advantage of something called beta-gamma coincidence, where an electron and a photon with characteristic energies or energy ranges are released in coincidence with each other. And so that's what our detection systems, the TE, CZT, and the CAS system, utilize. So what do we want in a detection system that is in this international monitoring system? Well, we want it to be able to operate long-term and autonomously because these systems are placed all around the world. We want to have high resolution at room temperature because high resolution means tight ROIs, and ROI is a region of interest, and that's a range of electron and photon energies wherein we look for coincident events. Now, smaller ROIs, if you have a smaller ROI, you have reduced overlap between ROIs from these different isotopes, and not only do you have less overlap, you have less of a chance of a background coincidence occurring within these ROIs. And so if you have smaller ROIs, you can have a better minimum detectable concentration with your detection system, and that means a better detection system overall. We want it to be compact, low power, and low cost, and of course we want to have good background and noise rejection. Good background rejection to increase our minimum detectable concentration, and good noise rejection because if you have low noise system, you can detect low energy radiation, and that's extremely important with a lot of these radioxenons. They release 30 keV X-rays, and so we need to be able to see those. So just some results from our original prototype, the TE-CZT. We used two coplanar CZTs surrounding a single gas cell. Again, we used CZT because it's got high resolution. We want those tight ROIs. It's got room temperature operation. We chose coplanar over something like pixelated because it uses simple readout electronics. And then we chose CZT because it minimizes memory effect. Now, memory effect is when you have the diffusion of xenon into the surrounding material. And these xenons, after you flush out the gas cell, the xenon will stay in the material that it's diffused into and decay. And this causes worse MDCs. Now, this doesn't happen as much with solid-state detectors as it does with, say, plastics. And so we used this in order to avoid memory effect as much as possible. For our processing, we use a dual-channel digital pulse processor with an FPGA that does coincidence discrimination on board, and this allows for extremely fast processing. It flags coincident events and then sends these coincident events to MATLAB user interface where they can be processed. So very, very fast. And so, yeah, here are some of the results. Here's from Xenon 135. Now, what we expect to see is we expect to see beta spectrum from 0 to 905 keV, and we expect both of these spectra to be located at 250 keV in coincidence with the 250 keV gamma. And that's exactly what we see. We also see this diagonal line here, and this is associated with full energy depositions between the two detectors from Compton events. And so if you sum up the X and the Y coordinates here, they'll sum up to 250 keV, and you can actually use this line to calibrate your system, which is what we did. Here are some results from Xenon 133 and 133M. Now, once again, we expect to see lines from 0 to 346 keV from the beta spectrum, and we expect these lines to be located at 30 keV and 81 keV in coincidence with the X-ray and the gamma release. And once again, that's exactly what we see. We also expect to see little blobs where the conversion electron from xenon 133M is in coincidence with the 30 keV X-ray. And we do see those blobs in the middle of the beta spectrum located at 30 keV. Now, we also see a region at low energies of coincidence events between 45 keV conversion electron, 30 keV X-rays, and beta spectra. And it's kind of hard to resolve what's going on here, and it's because our system isn't particularly good at low energy resolutions, and that's something we try to rectify in our new prototype system, the CASP system. Here are results from xenon 131. Once again, we expect to see a blob area at 30 keV and 129 keV, that coincidence, and that is what we see. We see backscatter coincidence events between the two detecting mediums. And something we see with xenon 131M, and this is a big impetus for the CASP system, is we see incomplete energy deposition from these conversion electrons, and that occurs when the conversion electron, it goes into one of the media and it scatters out and it doesn't deposit all its energy, but the X-ray, it's still in coincidence with this X-ray, and so you get the spreading of these regions of interest, and that can cause overlap with other ROIs, and it gives us a worse MDC. And so this is not something we want to see, and it inspired us to make the CASP system. Anyway, here's some resolutions from the TE-CZT, and I've highlighted the best results of each resolution, as well as background count rates in comparison to some other radioxenon detection systems. And as you can see, the TE-CZT performs remarkably well in all of these aspects, except for 30 keV. Again, 30 keV in those low energy regions we don't perform so well in. Here are some MDC calculations. Now, it's worth noting that these MDC calculations are optimistic. They're done based on single isotope injection. Each of these isotopes was injected separately, except xenon 133 and 133M. They were injected together. And so the MDCs calculated for our two-element CZT system are highlighted in blue here. And only for xenon 133 is below the minimum detectable concentration required by the CTBTO. However, this is largely because we only have 2 CZTs. If we have 6 CZTs, which are highlighted in red, we took the experimental data and we ran simulations, and we found that we got excellent MDC results for a 6 CZT system. So just some closing comments on this prototype. It shows that CZT is a very promising material for beta-gamma coincidence. It produces very low background count rates. We got some mixed results for MDC, but we can improve those results. And we got a few shortcomings due to the conversion electron backscattering, which has inspired us to the new design. So what do we want with this new design? Well, we want to mitigate this conversion electron backscatter, and we can do this by using a low Z material. These low Z materials, they're largely transparent to photons, but they're very good at detecting electrons. And so we make a cylindrical gas cell, and this will have the electrons fully deposit their energy inside this plastic, whereas the photons can pass out and go into our adjacent coplanar CZT and fully deposit their energy there. We want to be able to detect 30 keV, and so we made PCB mounted electronics. We mounted the entire system on one PCB, and this allows us to have a low noise system. We wanted to minimize those trace lengths. And on the top right there, you see our idealized system, and on the bottom right is a SolidWorks workup of the prototype system that we're using. And here's actual pictures of the CASP system. On the left here, you have our PCB. You see our array of SIPMs for light collection from the scintillator. And on the right, you actually see it assembled. You have the CZT and the holder mounted directly on the board. You have the scintillator stuck in there, and then you have the scintillators wrapped in Teflon, and you have the injection tube coming out the top. And so, just some materials. For gamma detection, we used a coplanar CZT from Redland. Our light collection from the scintillator, we used a 3x3 array of J-series SIPMs from Sensel. And we chose these because it's got really high pixel density, low noise, and you can pack them extremely close together. There's almost no border, so you have a really high effective light collection area. For beta and electron detection, we used a plastic scintillator from Elgin, EJ212. We chose this because it's very well matched to the J-series SIPMs, and our PCB was designed in-house. It's got dual channel readout, one channel for the CZT and one channel for the SIPM array. And so our readout, we're using the same digital pulse processor as we did for the TE-CZT system. It's got that FPGA for high-speed coincidence discrimination. And then we use a MATLAB user interface to adjust various parameters in the FPGA, such as coincidence, timing window, gain, et cetera, and this system allows us to have a real-time pulse display and energy display. And on the bottom right there, you can actually see what the user interface looks like. You've got the pulses and the spectra, and this is actually real data from xenon 135 measurement. So just for our experimental setup, we wrapped our scintillator in Teflon, painted the tube black, and then sealed everything in electrical tape to minimize as much light, external light, as possible. Then we put it all in a grounded metal box, so shielding out, again, as much light as possible, background, electrical interference, etc. And we can adjust things like the trimmer, and we can access the readouts from outside the box so we don't have to open it once we inject the radioxenon samples. So these radioxenon samples were created at Oregon State in our OSU trigger reactor. We made 3 milliliter samples of 130, 132, and 134, and we put them in the reactor for the times and with the neutron flux, as stated on this slide. Then we allowed the samples to decay for at least 12 hours before injecting in order to allow any impurities to decay away and also to reduce the activity so we didn't get a bunch of pileup in our system. So here's results from cesium-137. We needed to calibrate our detector, and we did this by running things in free running mode. And so we calibrated our CZT to the 662 keV peak, and then we used this Compton effect in order to calibrate the plastic running in coincidence mode. And so on the right here, we see the energy resolutions that we got. And we can already see that our 30 keV is significantly better than what we got in our TE-CZT system. Here are results from xenon 135. Now, what we expect, again, is to see the from 0 to 905 keV beta spectrum, and we expect this to be located at 250 keV gamma. And that is what we see. Now, this region over here, down at the bottom right, this is due to high energy electrons depositing their energy in the plastic, and this caused, and we didn't expect to see this, but it was a very large current draw, and our power supply we don't think can handle that much current draw. And so what this is causing is it's causing a coincidence between this real deposition and a surge of noise in the CZT leg. And so every high energy electron that is depositing energy in the plastic is causing a coincidence, whether it's real or not. And so that's what this noise region is. It's not necessarily real coincidences. And so we can apply a filter and get rid of this region. And that's what we did for xenon 133 and 133M. And so we don't see that anymore here, but what we do see is we see the beta spectra from 0 to 346 keV located at 30 keV and 81 keV. And we don't see much of 199, the conversion electron, from xenon 133M. And the reason why is because xenon 133M has a shorter half-life than xenon 133. And so when we were doing these characterization measurements in order to find the best parameters, we had these samples, a lot of it decayed away. And so by the time we actually injected xenon 133 and 133M, a lot of the xenon 133M had already decayed away. So we do see a little bit of of the conversion electron 199 from xenon 133M, but it's not very strong. And so when we do our second round of measurements, we're definitely going to be injecting this a lot sooner after irradiation in order to make sure that we can measure xenon 199. So just some concluding thoughts. We have designed a new prototype detection system that utilizes coplanar CCT, an array of SIPMs, and a plastic scintillator. It shows promising results as far as detection as far as beta gamma coincident detection is concerned. We've tested xenon 135, 133, and 133M. We've optimized various parameters such as trimmer settings, gain, so on and so forth, coincidence timing window. We've seen a significant improvement in resolution, 30 keV, in comparison to our TE-CZT system. However, we did see a strong memory effect. This is in large part due to us having the sample in the detection system for a very long time. When we do our second round of measurements, and in the field we wouldn't see this. We would inject the thing, do our measurement, and then remove the sample from the system. For our characterization measurements, they were in there for a while. So we're seeing strong memory effect now because it's a plastic, but in our next round of measurements, this will not be an issue. So we're going to be conducting a second round of measurements and do an analysis for all the radioxenon isotopes as well as background. We're going to use a different power supply to see how that affects the crosstalk between channels. We fully optimized these parameters, and so we expect to get excellent MDC calculations and results. And that's all I got. Thank you very much.
Here's the horizontal orientation where we can use a longitudinal beam through the container. So we modeled an assembly that has fuel pins.